Hi everybody, welcome back to YouTube Quick RT again. Today's topic is going to be about the normal incident plane waves. It's the continue from the last series 1, the uniform plane waves. Okay, first of all, from the last time I mentioned about all parameters that associate with meteors, which in the term of mu or epsilon and sigma. This will give you the propagation constant, gamma, and also intrinsic impedance of a meteor. Okay, so that seems to be explain the property of waves in the term of air, grammar. For this one, we will move on to what we call the normal incident of uniform plane waves on plane boundaries. From the pictures here, I put the media number 1 and media number 2 with the media property of mu1, epsilon 1, and sigma 1. Same thing as the media number 2, we're going to have mu2, epsilon 2, and sigma 2. What we're going to do is that we're going to write equations for electric fields and equation for magnetic fields. And from the picture here, I have our incident electromagnetic wave are coming from the media number 1 and go through the media number 2 and reflected back at I use the subscript R as reflected, and then also have transmitted I represent by the subscript T. Okay, so what we're going to do is that we're going to write down this one. You have our electromagnetic field, right? And also you have our magnetic field, and this one represented by I. So what we're going to do, we're going to write equation for the reflected electromagnetic field, and also transmitted electromagnetic fields or electromagnetic waves. Alright, let's start with the assign the rectangular coordinate here. In case I have the electromagnetic waves propagate from the left to the right, as in the picture here, and then I have the electric field component and the magnetic field component, and you know the relation, the Poynting vector P, which is the transfer the energy of electromagnetic wave, it's equal to E cross H. So you know exactly, for example, if your E has the component of X and H has the component of Y, so you try to cross vector AX cross AY, and then you're going to end up with P to be PZ in the direction of Z. Now since we already mentioned about the parameter eta intrinsic impedance of a meteor, and gamma is propagation constant, this is has the real part to be alpha, or the attenuation constant, and J beta, this is the imaginary part. Then beta is represent the phase constant. So what we are doing here, if I start with the incident electric field EI, which has the only X component, and then moving the electromagnetic wave is moving in the positive z direction, which is represented by this term, and EI0 is the amplitude of the incident electric field. Okay, and then you represent gamma 1 by alpha 1 plus j beta 1, and alpha 1 is the show you how the magnitude of incident electric field is going to be attenuated. It's depend on alpha 1 when it get deep into a meteor, and for beta 1 is going to tell you how much the phase difference is going to be. Okay, so there are so many things here that you can interpret from the field equation. Same thing as the HI, I have incident magnetic field equal to HI0 exponential negative gamma 1 z, and has the component only y component. And as you know, the relation between E and H, as I mentioned earlier, is simply equal to the intrinsic impedance of the meteor. So I can write the amplitude of the magnetic field to be EI0 over eta 1. Okay. When subscript 1 is in the media 1, and what we're going to do is that we're going to write down equation for reflected electric field, reflected magnetic field, transmitted electric field, and transmitted magnetic field. Okay. So let's see what's going on in meteors. Well, to be able to find ER, HR, ET, HT, we're going to define what we call reflection coefficient, which is equal to the ratio between reflected field over incident field, and also define tau as the transmitted coefficient, which is equal to ET over EI, and also your reflection coefficient is going to be in the term of eta 2 and eta 1, and eta 1 is the intrinsic impedance in the media number 1, and eta 2 is the intrinsic impedance of the media number 2. So you can find the reflection coefficient from eta 2 minus eta 1 over eta 2 plus eta 1. Okay, and you already know how to find eta. It's equal to square root of j omega mu over sigma plus j omega epsilon. Okay, we will work on that. And for tau, it's equal to eta 2 over eta 2 plus eta 1. And both reflection coefficient and transmitted coefficient is going to be written in the term of the magnitude and the phase. And they also have the relation between reflection coefficient and the transmission coefficient as the tau equal to 1 plus rho. The way I prove this one here, look at the boundary here. You have the media number 1 and you have media number 2. At the media number 1, you know that you have EI and ER. And you start from EI plus ER equal to ET. The incident field plus reflected field equal to transmitted field. and you represent ER by rho multiplied by EI, and you represent ET by tau multiplied by EI. So you just divide the equation by EI, you end up with 1 plus rho equal to tau, or the transmission coefficient is going to be equal to 1 plus reflection coefficient. Now if I assign the axis to be like this one here, x, y, z, and you look at two different meteors. We start from the step 1, EI equal to EM, which is the amplitude of incident electric field, multiplied by E to the power negative R gamma 1 Z, and AX choice has the component in only in X component. When you have electromagnetic wave incident on the boundary, and part of it will reflect back, and then part of it will transmit it to the meteor number 2. And keep in mind that this is, I just start with the normal incident plane wave. The normal is meaner is make a incident directly to the boundary of two meteors. So this one is make the angle to be 90 degree. Now step number 2, if I want to find a reflected electric field, I can write this one in a term rho, which is the reflection coefficient multiplied by EM, which is EM is the amplitude of incident electric field, and then multiplied by exponential plus gamma 1 Z, and still have the component X. But you can see the sign here is going to change from negative gamma 1 Z become positive gamma 1 Z, because the electromagnetic wave is moving in the opposite direction when it's reflect back. Okay, so don't forget the sign here. And step number 3, you can write the transmitted electric field is equal to the transmission coefficient tau multiplied by EM, and then multiplied by exponential negative gamma 2 Z. You have the negative sign here because the electromagnetic waves is moving in the negative Z direction. Actually this one up, sorry, this is the actually represented by moving in the positive Z direction. Alright, I have this one wrong, so your Z here is supposed to be plus right here, so you need to change all the system. Sorry for my mistake. And don't forget to change gamma to be gamma 2, because you are in the meteor number 2. This is very important. Okay, so we already have our EI, we already have ER and ET. Now what about the magnetic field? Well, when you have EI, you can write HI, incident magnetic field, which has a component of the Y component, and you use the relation E over H equal to what? Eta, correct? Intrinsic impedance of the meteor. So that's why I have our EM over eta 1 here, and still multiplied by exponential negative gamma 1 Z, but this one have the component of Y. Okay, just take a look at this point. Since you know that your pointing vector does tell you the direction of the electromagnetic wave, uh, like propagate, P are equal to E or cross H. So you can check this one here. When E, you have the component in the AX, right, direction, and H, you have the component in the Y axis. So AX cross AY, you notice is end up to be a Z, and that's agree with what you have here. This represent the direction of the electromagnetic wave propagation. So this one is moving in the positive Z direction. This have to be related to each other. Okay. So now you already have HI. So what about HR? Reflected magnetic field. So your HR equal to ER over eta 1, because it's still in the media number 1. And you ER, you simply pick up the amplitude here, which is equal to rho EM. And when it's reflected back, this one change the sign from negative gamma 1 Z to be positive gamma 1 Z, and still have the component in the y direction. And now for a transmitted magnetic field, you do the same thing. It's become ET by area 2, right? Because you are in the media number 2. And the amplitude of the ET is the tau EM. And you multiply by exponential negative gamma 2 ZAY. The components still become AY. Okay, if you come back to check this one here, for P equal to E cross H, when E is has the component of what? Still X. So you put AX here, and you cross H. It's going to be your you have to end up with the P, which is become a negative AZ, right? Because it's reflect back. So this one have to be negative or AY to end up with negative AZ. So I should have the negative side here. Alright, sorry for my mistake. Alright. But later on, if you know that for the reflection coefficient, since the rho equal to eta 2 minus eta 1, and eta 2 plus eta 1, what happens is that eta can be a complex number. So your reflection coefficient can be also a complex number, and can be written in the form of the magnitude of the reflection coefficient and the phase angle, and also the transmission coefficient is equal to the magnitude and the phase angle. Okay, so you have get some idea about how to each the fields related to each other. So let's start writing the fields equation. Okay, let's first start with the incident electric field. You have the amplitude EM, exponential negative, this has to be a gamma 1 Z cosine omega t minus beta 1 Z AX. What about ER? Okay, let's move up there. So your ER, the amplitude has to be the reflection coefficient multiplied by EM. So you have this term. I put the absolute value here just to show you that we multiply only absolute value. But keep in mind that your rho equal to also have the phase anchor here. And then multiplying by exponential of plus gamma 1 z, because the electromagnetic wave is moving on the opposite direction of the incident electromagnetic wave. So, or this one is moving into the negative z direction. And now you take a look at this one. Since you have a rho with the phase anchor to come to play with the equation, and then you need to add the phase of the reflection coefficient into the equation, but the component still be the x component. Why you put the positive sign here into the phase? These all are the phase, right? Well, you know the relation between ER equal to rho EI. This is the incident electric field. When your rho is equal to the magnitude rho and the phase anchor. So that means you add up the phase anchor to the phase of EI. So that's why I have the positive side here to be your theta rho. Okay. And keep in mind here that your gamma 1 is to become alpha 1 plus j beta 1, when beta 1 is the phase constant and alpha 1 is attenuation constant. Will show you how fast that the electric field will be attenuated, okay, or how fast it will decreased. Next, the transmitted electric field is going to be equal to transmission coefficient multiplied by EM of the incident electric field, and the transmitted electromagnetic wave still moving in the positive z direction, so you have the negative side here, but your gamma have to change from gamma 1 to be gamma 2. And since your tau also have the phase anchor here, you need to add up the phase anchor theta tau into the cosine omega t minus beta 1 z, but you also need to change beta 1 to be beta 2. Okay, you have the negative beta 2 z is tell you that the electromagnetic waves still are moving in the positive z direction, and still have the component of the x component. Now let's take a look at the magnetic field. For HI, you have the relation is equal to EI over eta. So you do the same thing. You pick up EM, the amplitude of incident electric field, divide by the magnitude of your eta. This one is supposed to be eta 1. And you also have the phase of eta 1 come to play in the equation. But this one, the size, you use the negative sign. Why? Because the relation of HI and EI is HI equal to EI over eta 1 when you use the eta 1 equal to the magnitude and the phase anchor theta eta 1. You move up here, the phase is going to be the opposite, and then that's why you have the negative phase right here. Okay, and HI had a component in the Y component. Okay, so from now on you should be able to understand and to be able to write HR and HT, by your own. So HR equal to ER over eta 1, still in the media number 1, and ER is equal to the magnitude of reflection coefficient multiplied by EM, and you divide by the magnitude of eta 1, and this one multiplied by exponential the positive gamma 1z, because the reflected electromagnetic wave is moving to the negative z direction. And for the phase, you not only have theta rho because you have the reflection, right, coefficient you add up, but you subtract theta area 1 to the equation, and the component still in the this one's supposed to be negative ay, also, okay, as I mentioned earlier. And now for HT is equal to ET over eta 2, now in the meter number 2. So for tau, you add up the phase angle of the transmission coefficient, and also subtract the phase angle of your eta 2 from the equation. So that's why you end up with the whole phase look like this. Okay, so it's very important for you to understand how to write the field's equation, both electric field and magnetic field. The next one is the time average power density vector of the transmitted wave. I use SAV. It's the represent the average. T is the transmitted. And time average power density is equal to 1 over 2 the real part of the transmitted electric field cross the conjugate of a transmitted magnetic field, and you represent ET by tau EM exponential negative gamma 2z, and cross tau conjugate, because tau can be a complex number, and EM and exponential negative gamma 2 conjugate, same. Your gamma or propagation constant can be a complex number, and you divide by eta 2 conjugate, and then you end up with the time average power density to be equal to 1 over 2 EM square, and then the magnitude of transmission coefficient square over eta 2. This one's supposed to be I'm missing something here. Negative 2 gammas z, right? And cosine theta. So what this is supposed to be theta what? Is called to be your theta eta 2, correct? And then you have the direction of the time average power density vector in positive z direction, the same direction as electromagnetic waves propagates. Now take a look at the example. When you have two different meteors, one is the air and the other one is the ocean, you have the aircraft flying in the sky, and then you want to send a signal to a submarine which is there in the ocean. And if the aircraft send a signal with the electric field to be 1000 volt per meter into the ocean, and the submarine going to detect the signal, have the equipment with sensitivity is 10 microvolt per meter. This means this is the minimum electric field that the submarine can detect. And ask you what is the maximum depth of the submarine that it still be able to detect the signal with the magnitude of 10 microvolt per meter. Okay, and the aircraft send out the signal with the frequency 1 megahertz, and mu r and epsilon r sigma in both meteors are given. Alright, first of all, you need to check what type of meteors is, for the ocean here. As I talk in uniform plane wave series 1, compare the ratio sigma 2 over omega epsilon 2. If it's much greater than 1, the meteor is going to be a good conductor, and you can use equation to find eta and your grammar, the propagation constant, because you need to use the for equation. Okay, let's take a look quick how you're going to analyze the problem here. Well, at the boundary between air and the ocean, you have start with the magnitude of the electric field ED0, which is the 1000 volt per meter. And when the signal transmit into the ocean, it will be attenuated because they have like sigma ray, and the magnitude of electric field with respect to the depth, I should put this one as Z, is going to correspond to ET0 multiplied by exponential negative gamma 2 Z, which is equal the magnitude of electric field at any Z, and you want to find the max, the depth that the submarine can be to be able to detect the signal, and the minimum electric field that the submarine can detect is 10 microvolt per meter. So you have to find the depth that the electric field is attenuated, go down to 10 microvolt per meter. Okay, so you need to use this equation. So where you need to find ET0 first. Sorry, this one is not 1000 volt, because that's supposed to be EI 0 is 1000 volt per meter. Okay, because the ET0 is going to relate to EI0 by this equation. ET0 is equal to the magnitude of transmission coefficient multiplied by EI0. So you need to find tau, the transmission coefficient, and also you need to find alpha 2, attenuation constant. Okay, let's work this out. For a good conductor, um, let's start with the, you need to find tau, right? So tau is equal to eta 2 over eta 1 plus eta 2. Eta 1 is the air, so let's take a look at eta 1. I rewrite the equation again for eta 1. J omega mu over sigma plus j omega epsilon. Since eta 1 is in the air, sigma equal to 0, or your eta 1 is the square root mu 0 over epsilon 0, and you know this is become intrinsic impedance of the free space. Now let's move on to find eta 2 to be able to find tau. When you already checked that the ocean is the good conductor with the frequency of 1 megahertz, you can approximate eta 2 to be square root omega mu over sigma, and the phase angle is the 45 degree. And you end up with the N2 eta 2 become 1.4 with the phase angle is 45 degree, and you can check alpha equal to beta. Simply multiply 1.4 by square root 2 over 2, which is come from cosine 45 degree. Right? Cosine 45 degree equal to sine 45 degree. Let's give you alpha equal to beta equal to 3.97 per meter. So you already have eta 2, and you already have eta 1. So you can find transmission coefficient. This is equal to 2 eta 2 over eta 2 plus eta 1. So you plug in the number here. This is the eta 2, and this is also eta 2, and your eta 1 is the intrinsic impedance of the free space, which is equal to 120 pi ohms. Finally, you have a reflection coefficient to be 7.41, 10 to a negative third, and the phase angle is 44.8 degree. Now you already have our tau, so you can find your ET0 by multiplying by transmission coefficient to the amplitude of incident electric field, which is equal to 1000 volt per meter. Okay, let's move on. When you have tau equal to 7.41, 10 to a negative third, 45 degree. So your ET0, that means the magnitude of magnetic field in the media number 2 at the boundary is going to be tau multiplied by EI0. So you multiply tau by EI0, so 1000 volt per meter. You have 7.41 volt per meter. So you look at the plot between Z here, deep inside the ocean. This is in the media number 2 already, in the ocean. You start with the magnitude of electric field, 7.41 volt per meter, and you're looking for the place. Okay, so you have our ED0 become 7.41 volt per meter, and if you see the plot, it starts from 7.41, and you want to find the depth of the submarine that it can get be able to get the minimum the electric field to be 10 microvolt per meter. So your Ez equal to ET0 exponential negative alpha 2 Z, or E alpha 2 Z equal to the ratio of ET0 over Ez, and you can find Z simply become 1 over alpha 2 ln of ET0 over Ez. So you plug in the number here. You have alpha 2 is 3.97 neighbor per meter, and you have ET0 start from 7.41, and you want to detect the signal 10 microvolt per meter. Then you end up with the depth to be 3.91 meter. Or in general form, when you have Z equal to 1 over alpha 2, or natural log of ET0 over Ez, and alpha 2 equal to square root omega mu sigma over 2. You want to how Z varies with the frequency. So you have omega right here equal to 2 pi f, and then you have Z is the 1 over square root pi f mu or sigma ln or ET0 over Ez. You take a look at this one. If you want the submarine to be able to go deeper into the ocean, your frequency have to be smaller and smaller, correct? So Z can be the larger number. That's how the one of application of military. Now let's move on. Let's find a few equations from the above situation. If I start with EI in the air, which is equal to EM cosine omega t minus beta 1 x, and has the Z component only. Take a look at this one here. This is in positive x direction, and then you can find beta 1 or equal to omega over the electromagnetic wave velocity, and omega equal to 2 pi f, and divide by c, right? Because in the air, the speed of electromagnetic wave in the air is about 3.0 10 to the 8, and EM is 1000. Now the reflected electric field is equal to the magnitude of reflection coefficient multiplied by EM, and since you have no phase of reflection coefficient, because your sigma equal to 0, your reflection coefficient has only the real number or the real part. So actually phi of theta of rho is equal to 0, and you have the magnitude of reflection coefficient to be 0.995. Oops, sorry. Alright, take it back. Sorry, rho is not only the real part, because you are equal to eta 2 minus eta 1 over eta 2 plus eta 1, and eta 2 is the complex number, so you end up with lower, as we worked out before. The phase of the rho is the 180 degree. Let's get back to the page number 3. have it somewhere here. I'm not sure it worked out on row. Alright, sorry, I did not show it for row. Well, your row is the equal to 0.995. Is you work out this one, eta 2 minus eta 1 divided by eta 2 plus eta 1. You end up to be that the magnitude of rho is the 0.995 and the phase angle is 180 degree. Okay, try to work out by yourself. Oh, I just have right here, sorry. This is the eta 2, this is eta 1, and I have a rho equal to 0.995 with the phase angle is 180 degree. Now for ET, you multiply the magnitude of transmission coefficient to the EM, and since you have your alpha 2 is not equal to 0, you need to multiply by exponential negative alpha 2x, and it's still moving in the positive direction here. But for ER, you don't have this term, right? Because in the median number 1, your alpha 1 is equal to 0. That's why you don't have exponential negative alpha 1x right here. But for this one, I think I did something wrong here. It's supposed to be the positive sign, right? Because the reflected electromagnetic wave has to go in the negative x direction, and this one also become positive. But for transmitted, it's still moving in the positive x direction. That's why I have negative beta 2x here. And also with the phase anchor of tau, you need to add up to the phase anchor here. So you have the magnitude of the transmission coefficient to be 7.1, 10 to a negative third, and the phase anchor of your tau is the 44.8. I have it somewhere here. Your tau is equal to 7.41, 10 to a negative third, and 45 degree of the phase. Alright, let's move on to the magnetic field equations. From the relation EOH equal to eta, we can write HI is still moving in a positive x direction. You have negative beta 1x here, and it's still in the median number 1. Since your eta 1 is the intrinsic impedance of the free space, which is equal to 120 pi, you have no phase anchor of phase becomes 0. So that's why you have 0 right here. Okay, and simply divide EM by the magnitude of eta 1. Now take a look at this one. Y is become the negative AY. Well, from the relation P equal to E cross H, and you have the direction of propagation of the electromagnetic wave in the positive x direction. So it's mean that you can write P in the term of PXAX, and your E is there in the direction of has the component AZ. So your H has to be negative AY to get the cross product become AX direction. right? So that's why I have negative AY here. So that's very important. Please keep that in mind. Now for HR, reflected magnetic field is equal to ER over eta 1. So you have eta 1 is 120 pi, and the magnitude of reflection coefficient is equal to 0.995. And R reflected, and you know that the electromagnetic wave is moving to the negative x direction. So that's why I have the positive side here. And beta still be beta 1 because in the median number 1. Now you take a look at the phase anchor here. You have the phase of rho, right? So that's why I have the positive, I add up. And the phase of eta 1, you have to subtract, So that's why I have negative theta of eta 1. But the phase anchor here is still to be 0. And theta rho is the 180 degree. But the direction of HR is have to be in the direction of positive AY. Do the same thing. Because the direction of propagation of reflected electromagnetic wave is in the direction of negative AX. And E still has the component EZAZ. So your HY has to be in the positive AY direction, right? Just compared to this one here. You can work out. Now our transmitted magnetic field, when it's in our meter number 2, you use subscript 2 here. HT is equal to ET over eta 2. And you also have this term exponential negative alpha 2x. And the phase, you need to add up the phase of the transmission coefficient, and you need to subtract, use the negative theta of eta 2, and the direction of HT is still in the direction of negative AY, same as HI, right? Okay, so this is how you come up with our field's equation. Now take a look at the overall pictures. You have the medium number 1, which is air, and the medium number 2, which is ocean. You have incoming, the incident electromagnetic wave EI here, EMI, and you have EI in Z direction. So your HI has to be in negative Y direction. And for reflected electromagnetic wave, you have a direction of propagation in the negative X direction. And your ER still at the component of AZ. So HR has to be in the direction of positive AY. That's why I have the vector, from the left to the right. Same as the transmitted electromagnetic wave. It's going to be the same as the incident electromagnetic wave. And if you take a look at the surface, the time varying power density PAV of transmitted wave is going to be equal to 1 over 2 EM square tau square over eta 2, and then cosine theta of eta 2. Okay, this is concern of transmitted electromagnetic wave. Just plug in the number, you end up with the P average to be 13.9 watt. And if you use another equation to calculate, because your tau square is simply become 1 minus the magnitude of the reflection coefficient square. You can represent, the PAV average of the transmitted wave by this equation as well. When the magnitude of rho is equal to 0.995 square, so you end up with the same number of the P average of transmitted electromagnetic wave. Now our P dissipation, you take a look at this one here. You're concerned over the skin depth or the depth of penetration. You're going to have the power dissipation in this region here of the skin depth simply equal to P average of transmitted at the boundary here minus P power dissipation average at x equal to delta or at the skin depth, or this is the P average of the transmitted electromagnetic wave, and minus at the skin depth you need to add up multiply by exponential negative 2 delta alpha 2, but delta multiply delta 2 is equal to 1 because it's the inverse proportional, so you minus exponential negative 2. You're going to have the power dissipation to be 12 watt. Okay. Okay, now take a look at the interesting case. You have incidence on the perfect conductors. What does it mean, the perfect conductors? The perfect conductors mean that you have a conductivity equal to infinity, okay, with no resistance. For example, just like superconductors. Well, you take a look at eta 2 from the equation, it gives you 0 because your sigma is infinity, right? You take a look at the reflection coefficient. You have the media number 1 and media number 2. When media number 2 is the perfect conductor, you find reflection coefficient to be eta 2 minus eta 1 over eta 2 plus eta 1. Since this one is 0 and this one is 0, so it gives you a negative 1. And for transmission coefficient equal to 2 eta 2 over eta 2 plus eta 1, because eta 2 is equal to 0, it gives you the transmission coefficient to be 0. And then use the same relation. E1 is the EI plus ER. When ER equal to EM exponential negative gamma 1 Z, and ER you simply multiply this one by rho, right? You add them up, but your rho is become negative 1, so that's I have a positive side here, showing to be a negative 1 here. Same as H1 equal to HI plus HR. It's become EM over eta 1 exponential negative gamma 1 Z minus EM over eta 1 exponential positive gamma 1 Z, and it has the component in AY direction, so it's as according to the picture here, you have incident electromagnetic wave and you have reflected electromagnetic wave. Now let's take a look. If media number 1 is lossless, or sigma 1 equal to 0, gamma 1 equal to has only a imaginary part, or equal to J beta 1, your alpha 1 is equal to 0. Take a look at the equation here. EI equal to EM, and you have this term, and if you use the E to the power j theta equal to cosine theta plus j sine theta, this term is give you or become negative 2 and then sine beta 1 z, and if you write the electric field in the term of also in the time domain, is equal to the real part of E1 multiplied by exponential j omega t. When your E1 is the complex number here, so you pick up the complex number of e to the j omega t, which is the j sine theta or j sine omega t. So that's why you have the term sine omega t here multiplied by the term of sine beta 1 z, same as the magnetic field. H1 equal to em over eta 1 and multiplied by this term, and for this term you end up with 2 cosine beta 1 z, and with the time domain you will pick up the real part of h1 multiplied by exponential j omega t. Since h1 is the real number, so you pick up the real number of this term, which is become cosine omega t. You have h1 become 2 em over eta 1 cosine beta 1 z cosine omega t. This is cosine beta 1 z. So it looks like a static wave, right? So I end up with a diagram for E1 and H1 like this. For this one is the perfect conductor. You have electromagnetic wave propagation from air to a perfect conductor. Then you have E1 equal to 2m sine beta 1 z, and you plot if you have the amplitude to be 2m for the electric field, and then with the function sine beta 1 z, when this one is like z axis, when z equal to 0 is give you 0, and then you end up with a plot like this. And for magnetic field, corresponds to this equation. You have the amplitude to be 2em over eta 1 with the function cosine beta 1 z, so it starts from 1 here. Okay, so this all about the normal incident of the plane waves. And next one we're going to talk about the oblique incident. What does it mean, the oblique incident? This means it's going to have to be more complicated system. You're not talking about the normal incident of the plane wave. So you have the media number 1 here, and you have the media number 2, and this is the normal line here. For this YouTube, we're talking about a normal incident plane wave, right? But later on, we're going to talk about oblique incident plane wave. So your theta here is not equal to 0. It's going to reflect back this way. And also in the media number 2, it's going to be deviate a little bit, or they have like reflection. with their theta 2 is not equal to theta 1. Okay, so I'll see you in our next YouTube.